Let us try to understand how to solve the example on the principal planes and stresses by using the Mohr circle method. As shown in the figure, this plane AB and CD, they are subjected to the tensile stress of 100 MPa. Similarly, these planes, they are subjected to the compressive stress of 60 MPa, that is plane AD, and plane BC, they are subjected to the compressive stress of 60 MPa. Apart from that, they are subjected to the complementary shear stress also. So this is the complementary shear stress acting in this direction, and this is acting in the opposite direction. So therefore, they are known as the complementary shear stresses. And the magnitude of this particular stress is 40 MPa. Similarly, on this plane, the tangential or shear stresses, complementary shear stresses which are acting, they are also of the same magnitude always. So that is 40 MPa as shown over here. But the stress which is acting, normal stress which is acting over here is the compressive stress. So what we can say in this particular case is that, suppose we consider this plane AB, correct? It is subjected to the tensile stress, that is 100 MPa, and the complementary shear stress of 40 MPa. Now you can see this particular complementary shear stress, this direction and this direction. So it is producing the anti-clockwise moment in this particular case, and therefore this shear stress is considered as a negative shear stress. Whereas if you consider these two parallel planes, right, then this particular shear stress, complementary shear stress, the pair of the complementary shear stresses, they are producing the clockwise moment, right, as shown over here. Therefore, they are positive. So we can say that on this plane, this is the tensile stress, normal stress is the tensile stress, hence it is positive. Whereas this shear stress, complementary shear stresses, they are negative because they are producing the anti-clockwise moment over here. So therefore, if we choose some scale, say 1 centimeter is to 20 MPa, then 100 divided by 20, that is 5 centimeter, that is 5, and similarly 40 divided by 20, that is 2. So we can say that on these particular planes, we can draw a point such that the coordinates of that particular point are 5, minus 2. 5 for this particular tensile stress, which is positive, so 100 divided by 20, that is 5, and minus 2 for this complementary shear stress, which is producing the anti-clockwise moment, so 40 divided by 20, that is 2. But as it is producing anti-clockwise moment, we are considering that as minus 2. So 5, minus 2 will be our first point. Similarly, for these planes, right, we can consider this is a compressive stress, and as it is a compressive stress, it is negative. And what is the magnitude of that? It is 60 MPa. So 60 divided by 20, that is 3. So minus 3 because it is negative. Compressive stress, they are considered as negative. And complementary shear stress, they are producing clockwise moment, and their magnitude is 40 divided by 20, that is 2. But as it is producing clockwise moment, they are considered as positive. Now let us consider any plane EF within the material making an angle of say 30.5 degree with the vertical as shown over here, and we want to find out what are the stresses which are acting, normal stress acting on this place and tangential or shear stress that is acting on this particular plane. We'll also find out what is the major principal stress, what is the minor principal stress, what is the maximum shear stress, and apart from that we'll also find out what is the normal stress on the plane of maximum shear. So let us start with the construction procedure for this. So as we have discussed earlier, our first point is P, 5, minus 2, and another point is D, that is 3, minus 2. Now join these 2 points. They will cut this particular axis at this particular point. So let us assume that this point is E. With E as a center and EB or ED as a radius, draw the circle. Now we have drawn this particular circle. This is known as the Mohr circle. Now write down the coordinates for this particular point. So coordinates of these ends of the circle. So over here we are having the circle is touching over here. H is 5.49, 0. Similarly, I is minus 3.49, 0. These are indicating the major principal stress and minor principal stress. Similarly, if we draw a vertical axis passing through the center of the circle, that is a Mohr circle, then it will intersect the circle at point J, where the coordinates are 0.98, 4.49. So these are the coordinates indicating that the shear stress is maximum over here, because this is the maximum radius. And as we know that we are measuring the normal stresses along this x-axis and shear stress will be along the y-axis. Now let us mark the point L, right, on the circle such that this angle BEL is twice the angle. And what is the angle that we want to? The plane is making an angle of 30.5. So this angle will be double that particular angle. So the angle will be 61 degree. 30.5 multiplied by 2, that is 61 degree. So angle between B, E and L is 61 degree. And on this particular plane, we want to find out the normal stresses, shear stress and resultant stress. Now you can see the coordinate of this particular point. It is 4.71 and 2.54. So 4.71, that is the x coordinate indicating the normal stress. So 4.71 multiplied by the scale, that is 20, you will get this particular value. Similarly, 2.54, it is the y coordinate, and along the y-axis we are having the shear stresses or tangential stresses. So 2.54 multiplied by 20 will give the shear stress tau. Now we'll join this particular L with the origin, that is M, and we'll measure this particular length. So length ML is 5.35. So 5.35 multiplied by 20. This will give you the resultant stress that is acting on this particular plane. So in this way, we have calculated the normal stress, then shear stress as well as the resultant stresses. So this will complete our Mohr circle. Now we know that from this point up to this, that is OH or MH, we can say that. So either you can consider this as 00 or OH or MH. So it should be MH, that will be more proper over here. So that value is 5.49. So this distance MH is known as the major principal stress. So it is MH into scale. Okay, so we can say that it is, instead of O, we can use M over here, and here also we use M. So from this point, that is M point, up to this H point, the distance is 4.49 multiplied by the scale. You will get, this is the major principal stress. Similarly, from M up to this I point, the length is minus 3.49. So it indicates that it is a compressive stress. So 3.49, this value we have written over here, multiplied by the scale. So this is the minor principal stress. Similarly, we can find out what is the normal stress on the plane of maximum shear. So this is the maximum shear stress. You can see, because this is the axis along which the shear stress is measured, and this is the maximum value of the radius. The radius will go on decreasing, as you can see these vertical lines over here. Okay, so the shear stress is always maximum along this particular axis. So EJ will be the value of maximum shear stress, or EK will be the maximum value of the maximum shear stress. So EJ multiplied by, so value of EJ, the what we can say y coordinate is 4.49 multiplied by 20, so that will give the maximum shear stress. Now on this particular plane, what is the normal stress? That will be equal to MP. Okay. So here that particular value, okay, instead of this we can say that is MP. Okay. So this MP distance, this is the x coordinate, and that is equal to how much? It is 0.98. So 0.98 multiplied by 20. So this is the normal stress which is acting on this plane of maximum shear. So this is the plane of the maximum shear. So in this way we can calculate the various values by using the